All right, so for your next midterm exam, which is next Monday, I posted whatever you need to know for your midterm exam on our Brainlearn. It's a long list. I try to be as comprehensive as possible. So please read it so that you know what to expect for your midterm exam. And in there, as you can see, we started by looking at, when, what, and where the exam is going to take place. Basically the same room. Just come to lecture as you already did. If you're watching the recording, come to lecture on next Wednesday. And for exam policy, as stated in my syllabus, my exams are open book, open notes. You can bring anything on paper. You can bring your molecular kit. You cannot use anything electronic, unfortunately. All right, so if you have your tablet writing your lecture note, you want to print it out. So you have it on paper, no exceptions. You can use any kind of calculator you like. I doubt you'll need to do very complicated calculation, like calculating octet rule, but you can use any kind of calculator. And one little other option is during the exam will start precisely at noon. Your TA will be here, administer the exam. Make sure you sit like one seat aside from each other. We should have enough seats. And then precisely at 12:50, your TA will call you to stop. So when we call it, please just stop working on your exam, and then pass the exam to the front without moving. All right, after we collect the exam, we'll say you can go. But if you keep writing after we call the time, you'll lose 10 points. It's just not worth it, all right? So keep that in mind. The structure of the midterm is gonna have 4 different sections. You'll have 5 true and false, 5 multiple choices. You'll have 4 short answer problems. So the short answer problem will be your discussion worksheet type of question, right? We give you a molecule, ask you to draw the highest and lowest chair conformation of a molecule. Or we give a molecule with multiple stereo center, ask you to assign RS stereo configuration, etc. And at the end, we'll have one comprehensive question with multiple parts. All right, like what we did before, you have a complicated molecule, we can ask you all kinds of questions regarding that molecule. And study suggestions, well, practice. And for practice problems, you have your discussion worksheet. You have discussion worksheet from your other section. Chapter end problems. I listed a bunch of chapter end problems that I feel like are, I don't want to say good, but I feel like they're pretty educative. I'm not saying these are going to be questions on your exam, but they're just more educative than the other ones. And if you need help, we will have a buffer lecture next Monday. So basically next Monday, we'll go over all the materials that we covered from chapter 1 to chapter 3, which are your test range. And then we'll have questions for Q&A for any questions you may have next Monday. I'll be hosting office hour next Tuesday as well. And then your learning assistant are generous enough to offer additional review session on Sunday. So I think your learning assistant just texting me, it's going to be only in person in Young Hall 2033. So I'll take off that Zoom link. It will be only in person. And if you have any material related question, you might want, please do not email me. Instead, use the discussion board to ask those questions. Because this way, your other fellow students also see what you want to ask and also see our response to those questions. Okay, any questions before we go on? If you have any additional general question, you can also post them on the discussion board. That's all. Okay, so back to our lecture. So today we'll finish up on chapter 3, and your midterm exam 1 will be everything from chapter 1 to chapter 3. We will talk a little bit about acid and base chemistry in chapter 4 today, but those material will not be on midterm 1, it will be on midterm 2. All right, because I'm a little bit behind, I cannot risk this lecture, but at the same time, I don't want to rush chapters 4 into your midterm exam. So let's just finish up on chapter 3. So we went over this flow chart, if you remember, which is, well, basically everything you need to know about assigning chirality or deciding whether or not a molecule is chiral, achiral, whether the molecule has stereo center or chiral center, how to assign RS stereo configuration, how to draw Fischer projection, how to draw enantiomers and stereoisomers of a molecule. So far we did everything on paper, right? But as chemists, eventually we want to do experiments to be able to get an idea about what exactly does it mean in real life. So that comes to our next question, which is the property of enantiomers. So as we were saying, enantiomers are a mirror image to each other. They are not superimposable on top of each other, and thus enantiomers are different compounds. But they will have identical physical and chemical properties in an achiral environment. So the logic behind is the following. Like if we're just putting a bunch of water, which is achiral, like if you put a pair of enantiomers in that achiral environment, then there's no way of that achiral environment be able to tell you whether it's left-sided or right-sided, right? So a pair of enantiomer will have the same exact property in an achiral environment. Yes?
How are they different compounds if they're the same thing as split?
What do you mean by?
Because enantiomers aren't they the mirror reflection?
Yes.
So how are they different compounds? Don't they have the same connectivity?
Well, they have, so first of all, same connectivity doesn't mean they're the same compound. Stereoisomers are different compounds. Like if we think about biological world, we have lots of drugs that are chiral. So I'm gonna jump ahead a little bit on talking about why we care. Like if you think about a chirality, which is now we have a pair of enantiomers that are in a chiral environment, like maybe an enzymatic binding site, right? So the enzymatic binding site itself could be chiral. So if we look at the left-hand side, let's say the bottom one is my enzyme surface, and assuming we have different shapes, right? In reality, they're not square-shaped, but let's assuming you have different shapes on your enzyme surface. So these enzyme surface themselves is chiral. So as long as you have a matched chirality, you have the enantiomer, one enantiomer matching with the enzyme surface. But now if your drug is a different enantiomer, then it no longer matches the surface of the enzyme. So in a chiral environment, these enantiomers will behave differently. But in an achiral environment, like in water or in general solvent, then the enantiomers will have same properties because your achiral environment cannot distinguish their differences. Or the other way to put it, it's like if you put your left and right hand side into 2 cups of water, you feel the same. The water will always feel the same. But if you put it in a pair of gloves, so the gloves themselves are also chiral, right? So now you cannot put your left hand into your right glove or your right hand into your left glove because your glove is also chiral. I hope that makes a little bit more sense. Okay, so that's a general idea. And back to some other things. Diastereomers, on the other hand, these are simply completely different compounds. They have different physical properties, even in achiral environment. All right, so for physical properties, enantiomers are same in achiral environment, different in chiral environment. Diastereomers are just different in whatsoever. They're just different compounds. Yes?
So, at least in the chiral environment for an enantiomer, I know that for diastereomer, it's both different physical and different chemical. But for an enantiomer in the chiral environment, is it guaranteed to be both physical chemical different, or how do we determine is it either?
So for enantiomers in chiral environment, they will be different. So the enantiomers in any kind of chiral environment, they will behave differently. All right, so this is the physical property part. Next one, and then we want to know, as a chemist, how can we tell whether or not a compound contains like different chiral molecules, or how can we measure the ratio between enantiomers in a solvent. So in this case, the experiment we do is called rotation of the plane polarized light. I'm going to go over the general setup of these experiments. It's more important for you to know conceptually what they are and how do we get it there. I'm probably not going to test you heavily on the physics behind this experimental method. So bear with me a little bit. What we're looking at is that ordinary light. So if you're thinking about light, it's like going in any kind of directions when you have like a light bulb. So the light goes in any direction. The light wave just go in whatever direction it like. And then you can have a polarizing filter so that your light will vibrate only in parallel plane, or you get like plane wave coming out from the polarizing filter. All right, so we're processing the light so that the light will always be the plane polarized. And from there, whenever that plane polarized light meets an optically active molecule. So the definition of the optically active molecule is referred to a compound that rotates plane polarized light, which is a little bit jargon-like, or the other way to put it, we know that enantiomers are optically active. Because enantiomers in the achiral environment, they have the same physical property, we need something else so we can distinguish enantiomers. Diastereomers, on the other hand, their physical property is different, so we have more ways of separating diastereomers. But for enantiomers, it's harder, yes?
Is this experiment always being done in a chiral environment?
Yes. And in here, after the plane polarized light meets the optically active chiral molecule, the light will be tilted, or there's a rotation of the light. And we can measure the number of the rotation. And that gives us an idea about like what's in there, what's in our sample, how much these optically active molecules are there. And you can imagine when you have two different enantiomers, a pair of enantiomers, right? One of them is going to tilt the light to the left, the other is going to tilt the light to the right. And then the final observed tilted angle tells you information about the ratio of enantiomers in your sample. So far, so good? Okay. And then let's move on to see how exactly does chemists use this experiment to calculate what's the ratio of your enantiomer in the solution. So this part is more like conceptually it's important. So the next part is we're actually doing calculation. You might need to know that, and also it might come useful for you as a chemist later on. So optical activity calculations. When we say specific rotation, what we're saying is observed rotation when a pure sample is measured under specific condition. So this is the absolute, or the rotation of the light when you have an enantiomer pure compound, like 100% R or 100% S. Right, so on the top you have certain degree, on the bottom you have cell length and concentration. You'll have like what I said, you'll have tilted to the left or tilted to the right. So that's what we call the level rotatory or the dextrorotatory. So to the left or to the right. Now these rotatory, they'll have the same numeric number for your R and S enantiomer isomers, but your plus and minus doesn't necessarily correspond to the R and S stereo configuration. So there's no guarantee that R is always plus, S is always minus. There's no guarantee like that. The R and S do not correlate with plus and minus. But for pure samples, the actual number will be the same. And that's what we expect, right? As we were saying, enantiomers have the same physical property. The only difference is the direction. So it's either to the left or to the right, but to the same level. All right, yes?
I know this might basically be answered by what's up there, but is right always, you said like hardness, you don't have to correlate with plus and minus, so
Nope.
it doesn't matter if right or left, like left can be plus.
Okay, so left and right is basically minus and plus. That's just an easier way to say it. That's how, like this one is parallel, assuming, right? So you can tilt it to the left or tilt it to the right. That's your plus, minus. That doesn't matter.
Oh, so right is always plus and left?
Yeah, right is, well, tilting to the right is plus, tilting to the left is minus.
Okay.
But whether minus or plus, that's not correlates to ROS.
Okay, that makes sense.
Yes.
But getting like a plus and a minus correlates to the fact that you're in it.
Yes. So when you have two samples, assuming we have two samples at the same concentration, put it in the same container, right? I put it into my my device. I'll always get a, like say, plus X. I'll always get a minus X, and that X will be the same number. But it is still very useful. Now, assuming we have a mixture, and we want to know to what percentage we have one enantiomer over the other. So this experiment is a very useful tool for us to determine something called enantiomer isomeric axis. So here's what we have. So the measurement we're taking is called optical purity, or the way to put it is that's describing the composition of a mixture of enantiomers. All right, so now imagine you have a mixture of R and S enantiomers in a container. And we want to know what percentage is larger. I mean, we want to know what's the difference between these two enantiomers, whichever is higher. So in this case, the percentage optical purity is the alpha of the sample, or that's a specific rotation of the sample, divided by the specific rotation of your pure enantiomer. So again, this is something we're talking, like this one is parallel, right? So if you have 100% plus, so we're tilting to the right, so the 100% plus. But now instead of 100% plus, we're tilting it only to 80%. All right, so that tells me my sample doesn't contain 100% of that enantiomer pure item. It's like a ratio, it's a mixture. So this percentage optical purity is numerically the same as our enantiomer isomeric axis. Or the enantiomer isomeric axis is the difference between the percentage of two enantiomers in a mixture. All right, so the top one is experimentally you can measure it, and this experimental measurement gives us the value of enantiomer isomeric axis. All right, and EE, when we say enantiomer isomeric axis, that's the R minus S, or the difference of your stereoisomer over the total amount of your stereoisomer times 100%. In chemistry, we also often use something called enantiomer ratio, or enantiomeric ratio, or ER. So ER, that's just the ratio between your R or S or S to R. It doesn't matter which one you put in the front. That's just the ratio of your two enantiomers. Any questions before we move on to examples? And let's do one example together and see how do we apply it in real life. So let's assume we have a commercial synthesis, like a drug company. The synthesis is naproxen. So it's a non-steroidal anti-inflammatory drug, so NSAID. And we're giving you that in this mixture, the S enantiomer is in 97% EE. We're also telling you the specific rotation is 67%. So the question first is calculating the percentage of your R and S enantiomers in a sample of this mixture, which is, well, 97% EE. So this one is basically translating percentage EE into percentage ER. So there are different ways to do it. I mean, I tend to do it like, we say like percentage S plus percentage R equals to 100%. And percentage S minus percentage R is 97%. So that's your EE. That's your percentage EE. So what that tells me is solving this relationship, you get percentage S being 98.5, percentage R being 1.5. Or the other way to put it is you can add them together and divide it by 2, you get the percentage of the higher enantiomer. Okay, so what is my percentage EE? So my percentage EE is this one. All right, so what do we know? I know that my percentage S plus percentage R must be 100, or this bottom one is like 1, right? And on the top, this one is 97. So we know that my R minus S equals to 97, R plus S equals to 100. So if you add these two equations together, you get 2 times R equals to 197. So my R must be 98.5. You plug that R in equals to 98.5 back to any of the equation, you get percentage. Wait, I think I reversed it. It should be S, sorry. Sorry for the confusion. S, S, R, R, S, S. So we're telling you that S enantiomers in 97% EE means we have 97% more E than R in my mixture. So in this equation, this R and S, it's not 100% set. This one is whichever is higher number, which one is lower number. So in this equation, it doesn't matter if it's R minus S or S minus R. It's whichever is higher goes in the front. So you want your percentage EE is always a positive number. So far, so good? So that's the first question, translating your EE with ER. Next question, what is the percentage optical purity? Let me make some space here. So the percentage optical purity, this one is a number that is numerically identical to percentage EE. So it's just 97%. And what about the last one? So the last one is asking for the observed rotation. So in this question, we know what is my percentage optical purity, and we also know the rotation of a pure sample. So we're using this equation here. And plug in the numbers, this percentage optical purity, that's 97%, equals to the alpha of the sample that we're looking for, over the alpha of the pure enantiomer, which is given. So that's plus 67 degrees. You plug that into your calculator, you get your final answer to be 64.5 degrees. we can ask the question a reverse order, right? So in this question, I can give you what is the observed alpha, what is the pure alpha, and ask you to calculate percentage EE of the mixture. So it's one way or the other. Okay, so this calls to the end to chapter 3. I'll take any questions you have on chapter 3 before we move on. Oh, okay, well, okay.
I'm still kind of confused where you got the 98.5% from.
This one?
Yeah.
Okay, so this equation, the EE, I'm just going to do it on the board. This might be easier. So your EE, percentage EE, on the top, you have the major initial isomer minus the minor initial isomer. On the bottom, you have your major initial isomer plus your minor initial isomer. All right. So in this question, what do we know? We know that my percentage EE is 97%. And we only have a pair of enantiomers, so my major minus plus minus, whatever that is, must add up to be 100. Or just 1. And on the top, that's your major minus minor. Right. So what do we know here? We know that my major plus minor equals to 100. We know my major minus minor equals to 97. Right. And taking these two formulas, adding up together, you can do it differently, but we can quickly solve it to be 2 major, and these two will cancel out, equals to 197%. You can solve for major equals to 98.5, which is 197 divided by 2. And the rest is 1 minus that. Yes?
For the 64.5 for the last one, when I did the math, I got 64.9.
My number could totally be wrong. You know, my math is not very good. But as long as you set up the calculation the same way, we should get the same answer. Yeah.
Oh, can you explain the calculation for C one more time?
For C,
Yeah, the observed.
so this one we're using the equation. Percentage optical purity equals to alpha of the sample. So that's the rotation of the sample. That's what we're looking for. Over the specific rotation of the pure enantiomer. And this one is given in the question here. All right, and just plug in numbers to get a result. Yes?
For like the alpha 25D, what is that telling us? Is that
So 25 is something specific for the test tube that you were using. This D actually tells you it's S, but I don't expect you to know. I'll make sure you know what that means.
okay.
Yes.
Is the optical, so you determine D by saying that the optical purity is identical to the 97%.
Mm-hmm.
So why is that? Why is optical purity identical to?
It's just given. It's just a fact for this class at least. If you dig into analytical chemistry, they have like proof to show why they're identical. Yep. All right. So that's it for chapter 3. Your midterm exam will cover everything from lecture 1 all the way to here. All right. We have like 20 more minutes. I'm going to quickly introduce acid-base chemistry. One more. Acid-base chemistry. But those acid-base chemistry will not on your midterm 1. They're fair game for midterm 2. Okay, one more question.
For nomenclature, is it going to be naming just like alpha
let's save those general questions for midterm exam for next Monday, which is a buffer lecture that I'll be here answering any questions you like. All right, so let's just get, is that specific to chirality?
Yeah.
Okay.
I don't know which one's R, which one's S.
We don't, we have to determine it from other ways. So from the optical measurement, we only tells you what's the major, what's the minor, and what's the difference between them, what's the ratio between them. But you have to determine the absolute stereo configuration from other methods.
Okay, so you just arbitrarily set it as R.
This one, we're just telling you the major one is S. Like maybe the experimentalists were good enough to grow a crystal out of it and see the absolute stereo configuration.
Yeah.
All right, so chapter 4, getting started a little bit. Okay. Yeah. Okay. So chapter 1, general nomenclature on chemistry, what is bonding, what is an atom. Chapter 2, structures of your molecule. Right? You have conformations, you have Newman conformation, you have chair conformation, you have nomenclature. Chapter 3, chirality. What is chirality? How to assign chirality, Fisher projections, RS, naming system. Chapter 4, we started to talk about chemicals reacting to each other. So chapter 4 are acid-base chemistry. So in entire chapter 4, we have several lectures on it. We'll go over basic theories of acid-base chemistry. We'll talk about pKa and also use that as a handle to introduce thermodynamics and also reaction mechanism. And at the very end, you'll be equipped with tools so you can quickly predict the acidity of a molecule simply based on its molecular structure. But let's do it one by one. So, basic things, terminologies. When we're talking about acid-base, especially the common Bronsted-Lowry acid-base, there are several terminologies. When we say something is a Bronsted acid, it's basically a proton donor. When we say something is a Bronsted base, we're saying that molecule is a proton acceptor. So for using the common H2O and also HCl, hydrochloric acid, as an example, we're having the lone pair on the oxygen, of water, attacking the hydrogen of HCl, breaking the chemical bond of your HCl, and form H3O plus and chlorine. Right, so in this process, on the left, my water is my base, my HCl is my acid. Right, so it's an acid-base reaction. It's an acid reacting with a base. It's relative, right? So HCl is more acidic than H2O. So in this reaction, your H2O is a base, your HCl is the acid. And what we're forming, H3O plus, or the product of this acid-base reaction, this is a conjugate acid of H2O, where chlorine minus is the conjugate base of HCl. So far, so good? And let's inherit some of the example from Dr. Pham's class. Now, this one is an acid-base reaction. You have some kind of alcohol reacting with a H plus. So when we do the everything like that, we're saying the OH, the lone pair of the OH, that's my proton acceptor. My H plus is my proton donor. Right? So this is my acid. This is my base. And what we're forming? Well, we're forming this one. And that's the conjugate acid of this molecule. We don't know what the conjugate base is because my H plus is, that's not known. All right, and same applies to something like when you're reacting a base, like a ammonia with water. So for example, in here, you can react my ammonia with water. So let me just redraw my H2O so I can do arrow pushing. So the lone pair of my ammonia reacting with grabbing the hydrogen of my OH, and the electrons in my OH get pushed onto the oxygen. So in this process, what is my base? Okay, anyone want to take a guess? What is my base?
NH3.
Yes, so this is my base. This is my acid. NH4 plus, thus is the conjugate base of NH3, where your OH minus is the conjugate acid of H2O. Oh, conjugate base, sorry. My bad. Sorry. So NH4 plus is a conjugate acid of NH3, and OH minus is conjugate base of H2O. Right. Some of the typical question we could ask you is, well, can you write the formula of the conjugate base of given molecules? So, for example, can you quickly write the conjugate base of chloric acid, nitric acid, and acetic acid? So for this one, we'll start, well, it's a conjugate base, so we're losing a proton, right? So my chloric acid donates a proton to form a conjugate base, which will be ClO3 minus. The nitric acid, that's the same. We have NO3 minus. Your acetic acid, that's a 3, CH3, COO minus. And to make a connection of the conjugate base to what we discussed before, now let's just pick a random one. Now from the conjugate base of acetic acid, can you write its Lewis dot diagram with all the resonance? All right, so that's like a common follow-up question of like, first you need to write out the conjugate base formula, and then you can write the Lewis dot diagram, and also all the resonance structure. So what does that look like? So we start from CH3, and then we have a carbon, which has 2 oxygens attached to the carbon. Okay, so let me not skip steps. So we have CH3, COO minus, so if we're doing the octet rule, we have 8 times 1, 2, 3, 4, plus 3 times 2, minus, well, 2 carbon, 2 oxygen, 3 hydrogen, and a minus charge, and times 1/2. We end up getting 32 plus 6 minus 20 minus 4, 1/2 of 38 minus 24, we're looking at 14 bonds. So in here we have 1, 2, 3, wait, is that 14 bonds? That's 7 bonds, sorry. We have 1, 2, 3, 4, 5, 6, 7. So we have a total of 7 chemical bonds in the Lewis dot diagram. And we add in the chemical bond, we add in the lone pairs. Clearly there exists another resonance structures. So we can do the arrow switching. And the way we do the arrow pushing is like this. All right, so this is a demonstration in the later time when we're linking different topics together. This could be a way of a part of the comprehensive problem. And plus a practice of Lewis dot diagram. Yes?
As far as the resonance structures, is that mainly reference when we move the double bond around?
Well, so for resonance structure, it's not moving the double bonds around, it's moving the electrons around. So consequently, you have different double bond and formal charges on the molecule. So it's the other way around. All right. So this is a general introduction, some terminologies of acid-base chemistry. And next up, we have arrow pushing in acid-base reaction. We already did a little bit of it. So we also did arrow pushing a little bit when we're looking at functional group. So now it's a good point of finally set some written rule for arrow pushing. So when we say arrow pushing, basically we're using these curved arrow to show movement of electrons. So when doing the arrow pushing, we're always pushing it from the electron source to electron acceptor. So from nucleophile to electrophile, right? So when we're doing the arrow pushing, you always start from some kind of electron source. That electron source can be a nucleophile or a proton acceptor, a Lewis base, a lone pair, a pi electron. So you always start your arrow from a electron donor or electron-rich moiety of your molecule. All right, and then the direction of the arrow pushing tells you where that electron got transferred to. And the end of your arrow pushing could be an electrophile, a proton donor, or a Lewis acid. So that's why when we do the arrow pushing, it goes from the lone pair of the OH to a proton. So when we look at a specific example, assuming on the left-hand side we have acetic acid, and then we have ammonia, right? We're forming the acetate ion, which is a conjugate base of acetic acid, and the ammonia ion, which is a conjugate acid of ammonia. We could ask you to use arrow pushing to show the movement of the electrons in this acid-base reaction. So how will that go? Right, we start from the electron source, which is a lone pair of my ammonia. You push it to here. So you're forming a new NH bond. But now my hydrogen is forming two bonds, right? So I want to push it again from the bond of your OH to the oxygen. So the electron is moving like this. You're forming a new bond between nitrogen and hydrogen. You're breaking the OH bond, and the electron got moved to the oxygen. And that's where the negative charge comes from. Right, so using arrow pushing to link your starting point and final point. Yes?
Is this more of an informal technique that helps with finding the answer, or would this be something that's required as a method in showing our work?
So this one is actually a very important tool in organic chemistry. When we start to talk about reaction mechanisms or how electrons are moving in between different steps. So I would say arrow pushing is something that's useful when you're trying to derive what is happening in an organic chemistry reaction. So following that topic, we'll do a demonstration here, right? So this is, again, inherent from our previous lecture. If you think about this one, we look at what we have. You have an alcohol, you have an alkyl alcohol, right? In this process, arrow pushing can direct us how will it take place. Now in here, when you put these two together, what will happen? It's basically an acid-base reaction. You have some electron-rich group, like lone pairs of your oxygen, acting as the Bronsted base. You have a H plus acting as a Bronsted acid. Right, so we do the arrow pushing, and after the arrow pushing, you can predict what comes out from this single elementary step, from this single electron movement. Well, in this case, we're only having the lone pair on the oxygen interact with the proton. So we're forming a new OH bond. Or the result comes to be, well, oxygen, hydrogen, and plus. Right. And something else can happen that's a little bit beyond what we have, but with enough knowledge, you can think about maybe something else will come. with one of the hydrogens here. And like grabbing this one and push it. That's way more complicated than I wanted to know. But I mean, from here, like later on, we'll use it to elucidate how reaction mechanisms take place. But for now, we'll just focus on acid-base chemistry. All right. The next question comes is, well, what is the site of protonation? When you have multiple nucleophilic parts, which one of these nucleophilic sites will be protonated? So again, using arrow pushing, but using arrow pushing to predict the product, and based on the stability of the product, we'll know which reaction is more likely to take place. All right, so let's do this example together. I'm telling you from the left-hand side, we have what's that functional group? Is it? Okay, so this is a carboxylic acid. All right, and in this case, what we do? So we're moving it. We have two different lone pairs that can potentially interact with your HCl. So let's say we start from this one. We do the arrow pushing. We're forming the conjugate acid of your carboxylic acid and the HCl minus, the Cl minus, the conjugate base of your HCl. Now, it's not like you cannot draw a resonance structure, but this resonance structure is like really high in energy. So if we're doing the resonance, arrow pushing for the resonance structure, what we're doing is we're breaking this bond, right? So the electrons in that bond that's like go to your oxygen. And we're forming these charge separated species, which is not even a valid resonance. So this is one option. The other option is we could use this carbonyl carbon to attack the hydrogen and break the HCl bonds. All right, and in this arrow pushing, we're forming a new OH bond on the carbonyl carbon, and this will be stabilized via this interaction. I'm just connecting these two. The middle one is not a valid one. Yes?
So that one we don't know is not the same thing where it should have two hydrogens and then a plus charge?
Yes, I'm missing a hydrogen there. You see, I'm not your most careful chemistry professor. Okay. Nevertheless, so in this case, this is a demonstration of, okay, so now we look at the product from these two arrow pushing processes. This one is not resonance stabilized, but the bottom one is resonance stabilized. So when we're actually looking at selectivity for these acid-base reactions, which site will get protonated first? Right, so the carbonyl carbon will be more likely to be protonated because we're forming these more stable products. Yes?
Is the bottom like considered your major?
These two are my major. This one is just not correct. I think I'm making a mistake somewhere. So just don't worry about it. And in addition, yeah.
Sorry. So those two are your major. Would you like, since you have that one is the most stable, you wouldn't consider the other ones?
Don't bother about those charge separated resonance structures. Like if you're looking at these two, this one has too many charges. Like you're manually breaking a single bond into two separate charge species, right? So this is not even a good resonance structure, judging by the criteria we learned in chapter 1.
So that wouldn't be resonance. Like the top one would not.
This one is not even a good resonance structure.
What about the other one?
This one is a product. This one is valid.
So even if we go with the bottom one, and things are going to happen, would that top one be a resonance of that?
So these two are different molecules. So keep in mind, resonance structures, we're only moving electrons. We cannot move atoms around. All right, so on top of lone pairs, one more thing. On top of lone pairs, remember my alkene pi bonds can also act as nucleophiles. So in this case, we can do the same kind of arrow pushing like what we did before. You start from a nucleophile, you're adding it to a electrophile, right? So the lone pair here, we can add it to a Bronsted acid, broke the chemical bond. Now this carbocation becomes my conjugate acid of the alkene. Right, the same applies to the bottom one. The alkene attacks the hydrogen, the electron in the bond go to the chlorine, and this becomes a conjugate acid. So arrow pushing is a very useful tool to connecting your reactant and product, and also direct us to visualize how does that reaction take place. Where does the electron movement go? All right, I'll see you on Monday.